Hey YouTube, it's Dimitri, and today we're going to do back propagation. So it's been a while, but I did forward propagation, so if you haven't done that video yet, please go back. I'll put like a little link above and some in the descriptions, but you need to watch the forward propagation first. This video is going to cover back propagation. If you loop forwards and backward propagation, that's the learning process for fitting a final model for a neural network. But let's just dive on in here. I'll try to make this as simple as possible. It's not too complicated, but there are a few things you need to know to do this correctly. Okay, so first things first here, let's just talk about what is gradient descent. So these are going to be your errors. They're going to be some space, so they might be multi-dimensional. The errors are with respect to the different inputs and layers in your model. But just simply talking about this, your errors might look something like this, okay? And the goal here is finding the spot on this plane of errors that has the minimum point. So, for example, when you do neural networks, you set all of your weights and your biases randomly, and then you need to actually fit the model, and then you should go back and reset them randomly again and rerun your model. The reason being is that if you start off and you pick some random weights, and let's say your weights put your error here, okay? When you do back propagation, the goal is to actually move this dot, so where we're finding, and we're going to try to find the lowest point. We're looking for the global minimum of the errors here, so we can move this direction. This isn't possible, right? In all cases, it's not possible to find your global minimum, but doing this process, resetting your weights, the goal is to try to find this. Something else we're going to talk about in a second here is your learning rate. I'll typically denote this as LR. This is just going to be the number that we move by. So when you do back propagation, you might start here at this red dot, right? And then you might move and you might come down to here to this red dot. And then you apply your learning rate, which is the distance that you move with each time. Okay? The smaller the learning rate, the better, in the sense that you won't necessarily miss a small increment. Maybe there's a really steep drop somewhere in here, and you want to be able to go down here and catch this minimum. But also, having too small of a value can be a negative, in the sense that it can take a long time to find your minimum that we're looking for. And if it's too large, right, you might skip over. So you might start here at the same point, and if you skip, you might end up with one deviation here, ending with a dot here. And then maybe you skip again and you end up here. And hopefully at this point, right, it'd push you back down and you'd find your minimum. But sometimes if you have too large of a gap, right, you might start in our original point here, and then it might jump to somewhere over here. And then you might end up finding some minimum over here, right, if this line was to do something like this. But the issue is that you wouldn't be able to get this minimum that we're searching for. And I should note, again here, right, we can never find the global piece, and the reason is you might have this function that goes over here, and all of a sudden you have something like way down here. Maybe this is a true global minimum, but maybe we just never find it, okay? And this is very likely that you will never find it. We never are quite sure where the global minimum is, but in general, we're trying to find a minimum that we think is very good. And because of this, right, when we do this iteration multiple times, we end up actually resetting our weights and biases, as I mentioned, because we're hoping that we might start at a different location. We might find a better minimal error with the model, which means it's a better fitting model, but also it might be a truer model in relation to the problem we're solving. So that's gradient descent in a nutshell. Let's just dive on into the math here and go through the process of back propagation. Okay, so simply put, back propagation is only a few steps. So one, we need to calculate our errors, which we're going to do here in a second. Two, we need to find our slopes. Three, we need to calculate our delta. So, right, delta. And then 4 is apply the learning rate, which will also end up updating our weights, W, and our biases, B. Okay, so this is going to be kind of the steps that we're going to take to do the backpropagation. All right, so looking at the neural network here, we need to realize, for example, in this simple example, we have one output layer right here, we'll call it O. And then this is going to be our hidden layer, which is right here. And then finally, this is going to be our input. When we go through this process, we're going to have to do calculations for the output layer. Then we're going to have to go back and do errors and issue, right? The errors for the hidden layer, which is going to be the second one. And that will give us the update. If you were to do a larger network, so you had 2, 3, 4 layers of hidden layers, you're going to have to keep doing the same calculations for each layer moving backwards and then updating them. But in this simple example, we're just going to use one hidden layer, inputs, and an output layer. So to calculate, so step one here, right, this is going to be our errors. The errors of the output layer are going to be y, which is our actual values, minus our prediction. So we're just going to call this p for prediction. And this is going to give us our errors at that final output layer. So step 2 is going to be calculating the derivative of our function here. So we'll just call this the derivative of f of x. So our function with respects to x. We're going to be using logistic or sigmoidal for our activation function. And if you remember, I'll put another link up above here as well, how we actually get to this. But the derivative of this is going to be x times 1 minus x. And this is going to be the derivative of the logistic function with respects to x. Like I mentioned, this is just going to be x times 1 minus x. Okay, so step 3 here is going to be calculating out delta. Okay, and to calculate our delta, what we're going to do is just take the slope times our errors here. And this is just going to give us delta. Okay, and then finally here, we're just going to do step 4. So step 4 is just going to be delta times our inputs, so we'll call these the weights, times, again, the learning rate here, which in this case, in our examples here, we're going to use 0.01, I believe. And then we're going to take this is going to be our adjustment, and then we're going to add this to the original weights. And this will give us our final updated weights. We'll do the same thing for the biases too, as you'll see here in a second. For the biases here, I should note it's going to be the sum of the matrix of your delta here times your learning rate, right? And this is going to be the adjustment for the beta or your biases here. And then we're going to add this to our original biases. So you guys, you could call this b of t, and this of b of t plus 1 since we're updating this. But that's how we're going to do this. That's kind of the simple math behind this. This is just doing the first layer. Again, we have to backpropagate now into the second layer, which we're going to do all this next cell here in a second to make it a little more clear. So to do this for the hidden layer here, we're going to need to do, this is going to be errors of your hidden layer, right? So step 1 again, this is just going to be delta from your output layer. So delta of output layer times your weights of your output layer. And like I mentioned, this is going to be the errors of the hidden layer, okay? And then step 2, as we mentioned, we're going to calculate the slope, but now in this case, it's going to be of the hidden layer. So again, you're going to have the slope here of the hidden layer, which is just going to be equal to, again, we're using logistic as the activation function, so we use that derivative. So it's going to be x times 1 minus x, but in this case, x is going to be equal to the hidden layer from before instead of the output layer, which we did when calculating the gradient for the output layer. Okay, and then step 3 is going to be calculating the delta for your hidden layer. And we do the exact same formula. It's going to be the slope of the hidden layer here times your errors from the hidden layer. So again, step 1 is going to be this one, And then step 2 is going to be this one. You multiply these together, and this will give you your delta for your hidden layer. And step 4, just like in the other case here, we're going to update these values with our learning rate. So it's going to be your delta of your hidden layer times the weights of the hidden layer times your learning rate. Okay, and this is going to be, again, the adjustment we're going to make. And we're going to add this adjustment to our original hidden layer weights. All right, and now updating your biases here with the learning rate. The updated biases is going to be the sum of the delta, but for the hidden layer, times the learning rate, which again, this is going to be our adjustment. And then we're going to add this adjustment to the original biases here. And that will give you your updated biases for the hidden layer. And then at that point, we're done. If you were to do this on many hidden layers, you need to go through these exact same steps again, but now for the next layer back, and then the next layer back, and you would just keep back propagating until you reach the very last hidden layer. And then we would take all these adjustments and we rerun forward propagation, and that will give us our new predictions. And then we can look at the predictions compared to the model actuals, so you get that model error again, and then you can repropagate again and again and again, and most software will output for you how many propagations it did, and then basically it will stop given a set number of propagations, or it will stop when some value is met. So like if the error no longer moves by 0.01 or 0.001, then it will just stop, and that will be your final model. So in practice, you would just do this propagation multiple times. You do the propagation to get your estimates, and then you'd redo the whole thing again, and you would take those errors and find which one has the lowest error. So you randomize your weights, do this process, estimation, find a model. Then you'd re-randomize your weights, do it again, all the propagation and everything, and get another model. Whichever one has the smallest one is typically the one you would choose, given that we found a better minimum for our errors. Okay, so now looking at this in Excel, this makes it a little clearer, a little easier, and you can actually play with the numbers and do this yourself. This piece up here is the forward propagation that we did in the original video. If we scroll down here a bit, this is going to be the back propagation I talked about. So step 1, calculate your errors. If you look in the cell here, we go up here, it's your actuals, which is Y, so A2, minus G15, which is going to be the output layer activation N. This is your final prediction from your forward propagation. So that's just calculating the errors of the output layer. Step 2 here is going to be calculating the slope. So again, we're using Logistic or the Sigmoid, and to do that, the derivative is going to be x times 1 minus x. You can see here that we take x, which is our output, our p, our prediction, and we multiply that by 1 minus x, so that output again. That will give us our slope. And then since we're already calculating the slope here, I like to just calculate the slope of the hidden layer at the same time. So I go in here and do the hidden layer activation. So that's going to be your inputs in your forward propagation, multiplied out by the weights and everything, and then applying that activation function, which is Logistic in our case, and then that's going to be the prediction for that node of the hidden layer. So it's just that times 1 minus that. And you can see here I do it for each individual cell. So this is every observation and every weight for this neural network here. So in our case, we have 6 that we need to calculate. And then after that, we calculate the deltas as I talked about. So the delta is just going to be the error times the slope. You can see this case we have error times the slope in Excel. And we do this for each observation that goes into the model. So there's going to be 3. And then next I like to calculate the errors for the hidden layer. So that's step 1 for the hidden layer process. Now you can't just use simple equations. You have to use matrix multiplication. So you can see here it's going to be your deltas of your output layer, which is a matrix. And we're going to multiply that by the transposed weights here of your output layer. So deltas times your weights, that's going to give you the errors of your hidden layer. And so this whole matrix will be calculated at one time in Excel because mmult, which is matrix multiplication, will do this as one process. And then the next step I do is now taking the deltas of the hidden layer. So the same process, we take our errors, we multiply it by our slope, This is a cell-by-cell function. So this is not matrix multiplication or matrix mathematics. And then finally here, we're just going to do all the new updated estimations. So now that we have all these calculations in the tables above, we're going to update them. So for the hidden layer, we take our delta of the hidden layer as matrix multiplication here, and we multiply that by our original inputs here. And then we multiply that by our learning rate, and that's going to be our adjustment that we're calculating. So what we're doing is we're just calculating, we're going to move just a little bit, and we're going to look at that slope, and we're going to try to go downhill. So we're doing gradient descent here. The gradient is going to be the slope. We're going to go downhill and try to get closer to that error, that global minimum if possible. And we're going to just move just a little bit. So that's that adjustment. That's that dot moving on that line. We'll move down just a little bit, and then we'll add these back to our original weights to make that adjustment. And this matrix here is going to be our new weights. And then you do the same thing for the output layer. So again, matrix multiplication, you take your deltas from the output here, and we multiply that by the hidden layer activation now. So that layer before it, these are going to be the inputs into this output. So you saw a second ago, for the hidden layer, we took the x1, x2, x3 as the inputs, and we multiplied that. For the output layer, the inputs are going to be the hidden layer, so we're going to take the hidden layer and multiply that by our deltas, and then we're going to multiply that by the learning rate, so we're going to move just a little bit. This new adjustment, again, is going to get added to our weights at output. And then finally, we're going to update the biases here. This is a little different. You just sum up all of the values in the delta matrix of the hidden layer. You multiply that by the learning rate, so we're going to adjust it just a little bit. And then we're going to take that adjustment and we're going to add that back to our biases in the hidden layer. And then finally, we're going to adjust the biases at the output. And again, we're going to take the sum here of our deltas at the output, and we're going to multiply that by the learning rate. So just a little bit of an adjustment. And then we're going to add that total adjustment here back to the biases at the output. So what you should take away from this is that if you look at the weights here, the new updated weights, they are quite similar to the original weights up here. So the top left one's negative 0.18. The new one is negative 0.17989. So it's basically the same. It's a little bit adjusted. And you can see the other ones as well. So 1.55 gets adjusted to 1.5503. And everything's going to get fudged just a little bit, okay? It's not guaranteed that you'll improve fit doing one iteration, but when you do multiple iterations, you'll see that it gets better and better and better. So in R and Python, when you see like that line that kind of plots out and then it bounces around a little bit, sometimes there's like a wiggle in it, and then it kind of flattens out. That's the error. That's what they're actually showing here. Okay, so now to look at this from a different perspective of actually going through and iterating. Our original errors are here. Again, you can look at these ones. These are the original errors. After we do this forward propagation, we calculate the errors, and then we make the adjustments. And if you go through and do forward propagation a second time now with the new weights, the new biases, and then you go back in and you calculate out your back propagation again and do your errors again, you'll see that your errors are actually getting a little bit smaller. So the original one was 0.04. Now we're at 0.038. So this observation is closer. The next one is 0.01205. This one is 0.010. So we're getting closer again. And then the final one is negative 0.03276. And this one's getting a little bit larger. It's negative 0.0345. Okay. So you're not always going to get smaller on every observation. But when you start iterating over time, most of them, if not all of them, will get smaller when you do 10, 20, 30, 40 iterations, however many it takes to actually get to that final model. And if you go through this process and you can actually test this, I use a function inside of R. I believe it's called the NeuralNet package in R. I'll put a link below as well. But you can actually start with these exact values of y, x1, x2. You can set up your weights and biases if you want. But if you iterate through it in R, you'll end up with this, what I call final output from the test output. And you can actually look at the math here, look at the weights. The weights are going to be quite similar because where we started at. But if you do this, you'll see that your new errors from this model are going to be actually smaller than the original ones. So let's just copy the original errors here and put them next to this one. Okay, so this was our original errors, and these are our final errors. And in this case, I'm just summing the errors to get some sort of value to look at. But you can see here the sum of the original errors is 0.019, and the sum of the final errors is negative 0.007. So when you do this forward and backward propagation in neural networks, you can see that the fit does actually improve quite a bit. And if you look at the sum of errors, so this was our original back propagation here. This will give you 0.00142. And the final one is 0.00129. So not a huge amount of improvement, but since we're normalized around 0 to 1 here, a very small range for the model, it should be a larger improvement based on the number we started with, percentage-wise. But anyways, I hope you guys find that video helpful. I'll provide a link below as well for the Excel so you guys can play with it and see exactly how it works. I hope you find the math in the beginning more intuitive and a little more simple. And then you can apply this to actual programming practices and kind of think about this more thoroughly, I guess, and apply this in a better setting. But anyways, don't forget to like, share, and subscribe. And as always, until next time.